yet it's used extensively now. If you Google Wheatstone bridge, you'll find, millions of hits. And it's used in a lot of modern transducers that are found in all kinds of industries. If I replace RL for a moment with a meter, think of this as a meter now, a current meter. We're going to think about the current that flows on each side of this, but let me just first redraw what this would look like, just drawn slightly different. Hello? Monday, for those of you in lab, Monday is the last lab. It's worth one full grade. It's a do or die. You build a circuit from a schematic and you measure the voltage across each element, current flow through each element. And if you get it correct, you maintain the grade that you're deserving at this point. If you get it wrong, you lose one grade. So that's how I separate the A's from the B's for the people who've been coming all the time. So don't miss a circuit that I can't tell you what it's going to be.
Okay.
It'll be like 6 resistors.
One that we picked, or
no, it's like 6 resistors, and there's no calculating or calculators. It's strictly measurement. So it's how to build the circuit and measure the quantities. Period. No calculating, no calculators, no T-spice, no neighbor. Your hand, your mind, your board, your resistors.
No T-spice, it's not exactly a wall.
Okay, back in the late 1800s, the way a resistor was measured was this idea. First of all, the bridge circuit has been historically drawn like this. But isn't this the identical circuit where if I straighten these resistors out, is this the actually clearer? You have kind of what looks like a series branch and another series branch with a bridge across between the two voltage dividers. So you can kind of think of it as this is a voltage divider, this is a voltage divider, dividing up the source voltage amongst here and here, dividing up the source voltage from here to here on these two series branches, but then you bridge across. Well, back in the day, they put a zero-centered, extremely sensitive meter in here, like 10 microamps negative and 10 microamps positive. So the meter zeros in the center. When current's flowing in one direction, the needle goes in one direction. When they split the current, the needle goes in the opposite direction. So it's centered at 0. When you put current flow in one direction, the needle moves to the left. Opposite direction, needle moves to the right. If you were to balance the bridge, it means that if you made the voltage at A with respect to a reference, and the voltage at B with respect to the same reference, if those two voltages were the same, how much current would bridge there? 0, because if VA equals VB, the difference in voltage between A and B is 0. If there's no voltage present between A and B, no current would flow, correct? So a balanced bridge exists when the voltage at B is identical to the voltage at A. Well, how could we make the voltage at B be identical to the voltage at A? If the ratio of R1 to R2 matched the ratio of R3 to R4. Resistors don't have to match, the ratio has to match. What I mean by that is, what if we had 5K and 5K? And I had 25K and 25K. Wouldn't 25K and 25K split the voltage equally? Wouldn't 5K and 5K split the voltage equally there? So you'd still get the same voltage there as there, because you'd be splitting whatever the source is equally. In other words, does it matter if it's 5K and 5K, or 10K and 10K, or 25K and 25K, or a million and a million? You're still going to split that voltage equally amongst the two resistors, aren't you? Okay, yes?
What's with the 3 dots?
That means therefore. That's a mathematical term. When you see, whenever you see 3 dots, that's the same as saying therefore. Sorry. Or it could be hieroglyphics.
I thought you were trying to draw
Or
a triangle,
it's
you know,
the way the alien spacecraft came when they visited me, they came in a formation like that. Anyways. So the ratio of R1 to R2 must equal the ratio of R3 to R4 to maintain VAB to be equal to 0. That's called a balanced bridge. Okay, so if you wanted to make a ohm meter back in the day, what you could do is put the unknown resistor here and make this a pot and calibrate a big dial that's connected to the pot with resistor values. And if you had different range, you'd select different resistors in this bridge. But here's the idea. What if I had a 5K here and a 5K here, and I had a 10K pot? Then I plug in an unknown resistor that happens to be 2K, because I know it. But it's an unknown resistor. You plug in a 2K there. What would I have to adjust that pot to get 0 current there? 2K. 2K. So didn't I just find out the value of the unknown resistor if I had a pot calibrated with a dial?
Yeah.
The neat thing about these Wheatstone bridges is it also works for capacitors and inductors. I can have a variable capacitor, put an unknown capacitor, put an AC generator, and adjust it to 0 volts AC, and I can know what the unknown capacitor was. I can do it with inductors. I could have an AC generator and inductor. Now, you don't know what the significance of that yet, but that's hard to do with a DC. You know, you can't do it like an ohm meter. You need to generate an AC signal and all this stuff. Well, the bridge was kind of a poor man's way, low-tech way of being able to find unknown capacitors, unknown resistors, unknown inductors by using ratios of capacitors, inductors, resistors, etc., AC generators. And here where you see, if I put now a 3K, wouldn't I have to readjust this to balance it again? I adjust it till I got 0. If I put a 3K unknown resistor here, obviously this would have to be adjusted to 3K to get the ratio of 3K to 3K to match the 5K to 5K. In other words, a 50% ratio, right? So that's how you measured resistors. Now in the early 1900s, there are these beautiful, they're typically like oak boxes, like the ones I saw. They're about this long, about this wide, had a sloping front and a top like that, a big old dial on front and a beautiful zero-centered meter. In a school I taught at a long time ago, the stockroom had a bunch of these left over that they had gotten donated years before. And we needed room in the stockroom, we threw them all in the trash, of course. And it was like sad to throw them in the trash. But guess what's happening on eBay? The price is starting to, does that curve of worth 0, starting on its upward rise. At some point, I think these things are going to be worth money because they were kind of works of art. They were made in the early 1900s, made great. They were just impeccably made. And so that was the first use really of the Wheatstone bridge, was to measure inductors, capacitors, and resistors. Now, in modern times, a Wheatstone bridge is very often in let's see how a Wheatstone bridge could operate a thermostat in a heating and air conditioning thing. What potentially could happen. Now, it doesn't necessarily have to be a bridge. There's another way of approaching it with op amps, but this is one way you could do it. In fact, one of the labs in this class, we ran out of labs because I missed the lab. I actually have people make a thermometer in lab. But what you do is you put a current meter here, and you make one of these resistors a temperature-dependent resistor. That's called a thermistor. You put a little T with a temperature sign or the degree sign next to it. It's called a thermistor. A thermistor is a temperature-dependent resistor. You can buy thermistors that are positive temperature coefficient and negative temperature coefficient. Positive temperature coefficient thermistors, as you increase the temperature, the resistance rises. In negative temperature coefficient thermistors, as you rise temperature, the resistance falls. You can buy both types. So you can buy materials whose resistance falls with rising temperature or rises with rising temperature. Either way, negative or positive temperature coefficient. They are resistors that are designed to change resistance with temperature. Any resistor changes resistance with temperature, believe it or not. In lab, you may not have realized that any resistor changes just a little bit with temperature. You must consider the thermal dynamics of components when they're in really hot environments. If you build a circuit that's operating, say, right next to the engine of a car, the thermal characteristics of the circuit have to be taken into consideration a lot more than just normal temperatures in rooms. Now, the temperature change of regular resistors is very tiny. They don't change much at all. The thermistor is the opposite. It's designed to change resistance with temperature. Okay, so if I put a thermistor there, and the thermistor is on the wall in a thermostat like that. So the thermostat's on the wall. Then instead of using a meter here, what you do, and you don't have to know this, you don't have to draw this or anything, but I bring this wire out and this wire out to what's called a differential amplifier. It's an amplifier where one terminal amplifies inverting and one terminal amplifies non-inverting, which effectively means is when you have a voltage rise into an inverting terminal, the output goes negative. When the voltage rises in a positive terminal, the output goes positive. So they go in alternate directions. It's similar to the idea that when you have a meter here, if current's going one way, the needle goes one way. If current's going the other way, the needle goes the opposite way, correct? Because current could go in either direction here, depending on whether this unbalancing is going up or down. So anyway, then you take this amplifier and drive a motor, and the motor is connected to louvers like this that are in your air conditioner. Now, the louvers like that can either be they're called registers. You can have a register where it opens and controls this register like a big square like that, or it can be inside a tube. You put like a butterfly valve that opens and closes to let air through, that kind of thing. So it's a variety of ways. And what you want to do is be able to open and close the louvers or open and close that valve to let air flow or not flow. Now here at Pierce, they have that central plant over there. As you drive into this lot, you see that, well, you don't drive in, but as I drive in the lot, you don't get to. There's this plant over there that's an air conditioning heating plant. And what they do is they pump the air through these tubes that are about this big in diameter, surrounded by insulation. They pump it to a bunch of classrooms throughout the school. So they have to bury these lines in the ground, and they're insulated. And the central plant makes air-conditioned air. It's pumped through these insulated pipes into the classroom. Well, how can you get different rooms to be different temperatures? It depends on how far away you're from the plant. You have a certain amount of loss in the lines and so forth. But how do you adjust the temperature in the room? Well, you use a thermistor. And then you put a pot here, and this is the adjustment of the thermistor. I shouldn't put a circle around it. I should just show it as a pot. You're educated. So you put a pot in there, a variable resistor. Now, isn't this going to be a ratio? What you want to do is adjust the pot so you get 0 volts. In other words, a balanced bridge when the room temperature is what you want it to be, like 72 degrees. So you adjust it to be balanced at 72 degrees. So whatever resistance that is, you adjust the knob till it's equal. You measure the voltage there at 0. You put providing no voltage to that motor. It's holding the air passage of the vents to whatever quiescent point it is. So initially, now of course you can calibrate this over time, but initially, wouldn't you just let the room get to what temperature you wanted it? You just adjust it. Pretty soon you get to a temperature that you like by turning a knob and unbalancing or balancing the bridge because of this. Okay, so I jumped ahead a little. So you adjust this to whatever, you come in and let's say it's just nice 72 degrees. Let's assume that this is balanced. You're in a hot day. The outside heat starts to heat up the room. The temperature in the room starts to rise. As the temperature in the room starts to rise, isn't that resistance changing? Because it's temperature-dependent resistance. As it starts to rise, it's no longer going to be balanced. The ratio is not going to be the same. It's either going to be this situation where B voltage is greater than A or A is greater than B. What you do is you make sure that when this is unbalanced, the polarity of voltage here is such that it starts to open the valve to let more air, open the louvers, open the register to let more air come into the room from its central air conditioning. So when it starts to get hot in the room, changes this balanced bridge to the point where it tells this motor to open the louvers a little more. That lets more cold air in the room. Doesn't the room therefore start to cool down? As the room cools down, could it pass that balance point and go the other direction, where it starts to get too cool? As it goes too cool, isn't this thermistor changing all the time? Doesn't it become unbalanced in the opposite direction? As it gets too cool, it swings past zero and goes the other direction. As it goes the other direction, the motor is a little DC, it's like a stepping motor, whatever you want to have, that just starts to close the valve, close the resistor a little bit, starts to stop the air. As you start stopping the air, what happens? The room starts to warm up again. As the room warms up again, it starts to go past balance, and at some point, what's going to happen? Isn't it effectively like, think of this current, when the current goes one way, you're opening the valve. As the current goes the other way, you're closing the valve. Isn't it self-regulating, because this is temperature dependent, but you decide at what temperature you want it to be where balance is. When it's truly balanced, the louvers don't move at all. But in all central air conditioning and heating systems, you have what's called hysteresis. As soon as the air conditioner runs, doesn't it cool off the house and it can go past where you want it? Then the air conditioner has to shut off. Then it waits for the room to warm. Then it warms up to a certain point, it turns back on again. The difference between where it turns on and off again, you can't have right away because it's cycling fast. If you made it too sensitive, as soon as it cooled down just a little bit, the air conditioner would shut off. Then as it warms up just a little bit, the air conditioner would go on again, which your air conditioner would be cycling too fast. So the hysteresis is how much you let it swing, how many degrees you let it swing back and forth.
Everything is internal to the thermostat or the whole assembly. It's not measuring it anywhere in the house, in the room.
No, the whole thing is that thermostat. That thermostat is determined. Now, in some fancier places, they have multiple thermostats around. So you can put multiple sensors and make sure that in different regions, and it can average the regions and so forth. But you see that this takes very little circuitry to do this kind of thing. So now, do you have to do that? No, you can use op amps that just wait for a thermistor to rise and make a voltage divider change, and then you have a computer that just senses when the voltage rises past a certain point, it switches it on. Then as it cools off, the thermistor changes. When it reaches a certain point, it turns on. That's like in automotive applications. The computer in an automobile, a lot of times it's simply, you have a thermistor that measures temperature change. When the temperature gets past a certain point, it tells the computer that has a analog to digital input. It converts it to a digital level that says, hey, something's going on here. And then the computer does whatever it has to do to compensate when the temperature has risen, that kind of thing. And that's very true in virtually all things nowadays. Thermistors are the main thing that judges whether temperature is high or low in anything. And then any electronic circuitry, like a lot of times we do these series parallel circuits. Can you see the significance of having a series parallel circuit where a certain resistor you have as a changing resistor based on temperature causes something to happen in the circuit? Your imagination can grow. But then, if you're interested in this, what you do is you Google thermostats and thermistors and Wheatstone bridge, and you'll get millions of hits. And you can see all different ways people creatively use this kind of thing. Now, another thing that can happen in a bridge circuit like this, since you have multiple elements that interact with each other, what you can do is put a temperature sensor in one part of the bridge and a pressure sensor in another part of the bridge, and balance occurs based on the condition of a pressure sensor and a temperature sensor. And only in a certain range of pressures and a certain range of temperatures do you have a balanced condition. So it's a much more exotic use of the bridge. But the neat thing about a bridge is it's self-regulating. You see the idea that it comes unbalanced in one way. If that causes something to happen that brings it back into balance again, you can have something unique happen. So bridge circuits are used extensively in transducers. Much more than I even thought in modern times. I thought this was getting obsolete. Then I went and Googled it and looked at some of the new transducers, and a heck of a lot of them are bridge circuits because it's kind of self-regulating. You know, the goal is you check the difference in voltage here, and it's these conditions. Either it's balanced or the voltage in one side is bigger than the other. And based on that, it's just based on changes in resistance. It's that simple. So it is a useful circuit. Now let's look at this unbalanced condition again. Unbalanced can be when the voltage from A with respect to ground, and let me just get rid of this stuff. And I'll just put a resistor here. But can you see that the voltage at A with respect to ground and B with respect to ground, if the voltage at B with respect to ground is bigger than A, wouldn't this be more positive than this side and you have that polarity? In other words, if voltage at B is bigger than A is higher, B is higher than A. That's positive and negative. But in this condition, if the ratio of resistors is such that A is bigger than B, and this is the positive side, and ground is the most negative side of the circuit, wouldn't that mean that A would be more positive than B? That's why that center meter goes one way or the other, depending on whether A is more positive or B is more positive. So you have these two possible conditions. Then the difference between the two is the voltage from A to B. Now, how could you determine the voltage across a resistor in the center of a bridge? Well, this falls right into Thevenin's, because isn't Thevenin's finding the open circuit output voltage between A and B? That is Thevenin. So let's just put some values in here and see what would happen. So I'll make sure it's unbalanced, and I'll get rid of these polarities. How about 2K and 4K here, and then I'll have 6K and 3K over here. I'm making sure it's unbalanced. And then let's put a load, RL, equal to 1K. Let's find the voltage drop across and current through that center resistor. So, first thing you do is find the A to B, which is the Thevenin, which is the open circuit output voltage between A and B. So you had to remove the load, right? And when you do that, here's the circuit. So I removed the load and labeled the points between those two, A and B. This line down here at the bottom is our reference line. So isn't VAB Thevenin? It's the open circuit output voltage between A and B. So I got to find VA, I got to find VB. How would I do that? Well, isn't VA the same as V2 with respect to ground? VA is the voltage across resistor 2. How would I find the voltage drop across resistor 2?
Source power? Or what's our voltage?
Oh, I didn't put one. That's a good idea. Let's put 20 volts. So, V2 is equal to the total times resistor 2 over resistor 1 plus resistor 2. Isn't this a voltage divider? You'd take the total voltage to this voltage divider times the resistor we're interested in, which is resistor 2, over the sum of the resistors. That's the voltage divider equation. Remember, the current divider was the opposite resistor on the top, or the sum of resistors times I total for the current divider. So it's the same resistor, the one you're interested in. Because remember what the voltage divider equation is all about. It's the ratio of resistors determines how the voltage splits. So that'd be 20 volts times resistor 2 is 4K, over 4K plus 2K, which is 6K. So on your calculator, you go 4 divided by 6, which is 2/3. 2/3 of 20 is what, 13.33, is that right? And what's VB? VB is the same as V4. The voltage at B with respect to ground is the voltage drop across resistor 4, isn't it? So VB is V4, and that's the total voltage times resistor 4 or resistor 3 plus resistor 4, or this voltage divider. this R over the sum of the R's times the total voltage. That's 20 volts times 3K over 6K plus 3K, which is 9K. Isn't that 1/3 of 20, which is 6.667 volts, isn't it? So what's VA B equal to? It's VA minus VB. What's the voltage potential difference between 2 points? If I'm finding the voltage at A with respect to B, it's VA minus VB because they have the same reference ground. So that's 13.33 volts minus 6.667 volts. And isn't that 6.667 volts? Check my math. Be sure? 6333? Well, 6.663?
Yeah.
Okay, but
From yeah.
13.33 minus 6.667
This is my
is
calculator.
6.663. Well, these I rounded, and that's rounded. If I carried these out, wouldn't it come out to 6.667? Because I'm just doing it from a theoretical point of view. Yeah? Because this is actually 16.66666. This is 13.3.
Would you mark this round to 6.6?
Hmm? What?
Would you mark this round to 6.6?
No, I wouldn't mark you wrong. And what is VA to B? Isn't that the open circuit output voltage, which we call Thevenin? Didn't we just find Thevenin? When you remove the load, isn't that resistor removed, and you look at the voltage from A to B, isn't that by definition Thevenin? Yes.
Yes, sir. We were able to do 2 voltage dividers.
Yes,
regardless.
because isn't this 20 volts across here and 20 volts across here? This is parallel. The voltage must be the same. So don't I have 20 volts here and 20 volts here no matter what, because those branches are in parallel. So could I think of this as a separate 20 volt series circuit, and this is a separate 20 volt series circuit? And so therefore I'm splitting voltage here according to the voltage divider equation. And this is 2K and 4K, so that's splitting it to, according to what we did there, is 2/3 of the voltage is across here. And over here, 1/3 of the voltage is across here. So this voltage with respect to ground and this voltage with respect to ground tells us that we then can find the difference between here and here. Isn't that this saying that VA, if I did it graphically, isn't VA up at around 13.33 volts with respect to ground, and VB is 6.67 volts. So what's VAB? It's the difference between the top building and the bottom building, isn't it? That's 6.667 volts. True? So that's what Thevenin is, the voltage that's between terminal A and terminal B. Yes?
Right there you're saying that voltage at A is equal to voltage at 2.
I can't hear you.
Are you saying that first one says voltage A is equal to voltage 2?
Correct.
What's voltage 2?
It's the voltage across this resistor 2. Because isn't VA with respect to ground, the voltage drop across resistor 2? And the voltage at B is the voltage drop across resistor 4. So the difference between the voltage at A and the voltage at B is the open circuit output voltage between A and B. Isn't it perspective? It's from here to here that you're measuring the voltage. There to there is this. Isn't it? From here to here. Make them sense? You have the look of either I don't care or I don't understand. Maybe it's a combination of both. Now we got to find R Thevenin. which is equal to the resistance between A and B, isn't it? This is not easy to see. You replace the power source with its internal resistance of 0. Here's point A. Here's point B. This is R1 of 2K, R2 of 4K, R3 of 6K, R4 of 3K. One second, because the hourly teacher, I think, left and the doors are all locked over here. When you're finding R Thevenin, isn't this the resistance between A and B, but you have to replace the power source with its internal resistance of 0. That then is difficult to see, because essentially to find R total, it's like putting in a power supply here. It pumps current into here and has to return there. When you pump current into there and try and follow where it goes to get back to there is not easy, because this is shorted over here. It does not become very clear, but redrawing the circuit makes it very clear. So this is what I'm going to do. I take the A. If I take this and extend it out, isn't that point still A? If I extend this out, move this B here, isn't that identical? All I did is extend the wire out. Now, I'm going to move it over here and show this is the A. It goes to two resistors, R1 and R2, that are connected together. So I'm bending them over. Here's R1 of 2K. Here is the 4K of resistor 2. Doesn't A go into where R1 and R2 come together, right? A goes into where R1 and R2 come together. Now the other end of R1 and R2, aren't they connected by a wire? So could I do this? Yeah. Now the other side, where B is, could I put B here and do the same thing? Show a resistor, R3, at 6K, and a resistor R4, which was 3K, and they come together at point B. Would you agree with that? The 6K and the 3K come together at B. Sure true? Now what about the other side of R3 and R4? Isn't there a 0 ohm path shorting R3 and R4 together? So is that true? It is, because there's a shorted path connecting R3 and R4. Now what about this shorted path that connected R1 and R2? Isn't it this wire? What's the shorted path that connected R3 and R4? It's the same shorted wire. Aren't these electrically the same wire? So can I do that? Yes, I can. Now, is that a solvable circuit? Yeah, sure. Now, if I grab these to unfold them, grab these and unfold them, it would be A coming into R2 of 4K and R1 of 2K, and this would be R4 of 3K and R2, no, R3 of 6K. So whereas I grab this and unfold it. Does it look like that? Now that's really easy to see. Isn't that two parallel resistors, R1 and R2 in parallel, added to R4 and R3 in parallel? Do these look in parallel? I don't think so. Not until you redraw it. It just so happens that R1 and R2 are in parallel, R3 and R4 are in parallel. So, then this would be two resistors. This would be the parallel combination of 2 and 4. 2 times 4 is 8, over 2 plus 4 is 6. It's 8 divided by 6, which is 1 point. What is it? Are you sure? Punch those buttons.
Oh, no, you're right. 1.33.
It sounds like 1.3. Just make sure. It's this late in the day, I will make a screwy mistake. Is that, it's these two, it's 2 times 4 is 8, or 2 plus 4 is 6. So what's 8 divided by 6 on your
2
calculator?
and 3 is.
Yeah, but don't talk.
1.3.
Yeah, it is. I just wanted to, because you first said 1.25 with such certainty, and I'm thinking, no, that's not it, but I wanted to make sure. So 1 point,
It's because he said it.
yeah, there you go. 1.33K. This would be some, like Rx, I'll call it. Now 3 6s are 18, over 3 plus 6 is 9. That's 2K, isn't it? So then, what is our final resistance from A to B? It's 2K plus 1.33, so it's 3.33K.
Yes,
Is that right?
correct, exactly.
So that's your RAB. What is this? R Thevenin, exactly. So this is 3.33K. So we got our R Thevenin, and we got our V Thevenin. What's our last step then?
Draw
Step
the
3. You draw the Thevenin equivalent. So you have a voltage source that's V A to B. It's V Thevenin, but what was V Thevenin? V A to B. And you have R Thevenin. So this is 3.33K, and V Thevenin was 6.67. And here's your A, and here's your B. A is more positive than B, isn't it? Make sure you put the polarity of your source here. And then we take our load resistor that we removed, this 1K, and we put it on there. So now we put that center resistor, our RL, we attach it here. This is our RL of 1K. Then when we find the voltage drop across RL, well, sure, it's the total voltage supply, which we call V Thevenin, times RL over R Thevenin plus RL. In other words, just don't get the label and get you freaked out. It's just fancy labeling, but isn't it the voltage here is the total voltage times this resistor over the sum of the resistors. So that's 6.667 volts times 1K over 4.33K. The sum of 1K plus 3.33 is 4.33. So it's about 1/4 of 6.667. What do you get? It's 1K over 4.33 equals then times 6.667. It's be about 1 point what? I'm not going to say it's too late for my daily work. 1 point what?
538 or 54.
You got the calculator.
Whatever you round it.
1.53?
Yeah, he's right.
Yeah.
1.534 volts, okay.
No, 1.5.
1.543? Something like that?
1.539, 1.54 milliamps.
No, we're finding volts.
Oh, shoot.
That's okay. So you have 1.54 volts here. Now how do you find the current through the load? Is the voltage drop across the load divided by the load? So That's easy. 1.540 volts divided by 1K is 1.54 milliamps, isn't it?
Oh.
So, without knowing Thevenin's, wouldn't you have to do mesh loop equations in this bridge? There's no other way. There's no way of combining resistors in series and parallel. So what you would have had to do, if you did not do this by Thevenin's, you'd have to make a loop here, a loop here, a loop here, 3 equations with 3 unknowns using simultaneous equations. You don't want to do that. Well, you do maybe. But with Thevenin's, you got an answer right away for that. And it's, once you understand it, it's not a lot of calculating really. This, to understand what the resistance is looking back, that can be a little intimidating. But once you know it, you know it's just R1 in parallel with R2 plus R3 in parallel with R4. You just have to remember that. You know, for a bridge.
So my one big question is, for this, does the Thevenin equivalents become different if you change? I think they don't. If you change RL. So if you change the load.
No, if you change the load, the Thevenin equivalent does not change. That's the point.
That's the whole point. Okay,
right. That's the point.
That's what I was.
The neat thing about Thevenin is, what if I put a different load here? Can I predict the result in this bridge? Yeah. These last, all I have to do.
Exactly. Okay.
Is change here. None of the rest of the stuff changes. That's the neat thing about Thevenin. Once you have the Thevenin equivalent, as I put different loads on here, I get different results without worrying about the rest of the bridge. Yes?
Is Thevenin's completely interchangeable with mesh? Like, you could use either in any of the same situations?
Well, when you say completely interchangeable, what you do is you have methods to solve problems. Sometimes multiple methods will give a result. But what should happen always, no matter which method you use, you damn well better get the same result, because it's a real circuit, right? In other words, if you're using one method, you get a different answer than another method, something's horribly wrong, true? Yeah. You must get the same answer no matter what method you use. So if you use mesh, you will get the same answer, won't you? Period.
But I mean, like in any scenario, are they both like 2 different methods that do all the same things, or is mesh useful for some things that Thevenin's can't do, or is Thevenin's?
Well, I will let you judge that for yourself as you get more proficient, because we haven't done Norton's yet, for example. The 4 methods I'm telling you are superposition, because it's so easy, it's so straightforward compared to other stuff you've done, and it illustrates the idea of current going in opposite direction, current going in the same direction, back routine. That's why I do superposition. Mesh, because all the other theorems are based on Kirchhoff's loop equations. If you do method of nodal analysis, Millman's theorem, other ones, they're just approaching it slightly different, but they all use simultaneous equations. So mesh will do what all those other ones will do. So I only teach mesh because why inundate your mind with 2 more methods that really don't help you? For example, PSpice uses nodal analysis. It finds the voltage at the nodes by doing a subtraction of voltage at one node from the other node to get the voltage across something, divided by the current to set up the equation. And if you were designing PSpice, it works out real nice, but as far as actually calculating, mesh is a little more efficient and easier, in my opinion. But you'll get the same result, and they're very similar. So you can, if you understand mesh, you can go in the book and read about nodal analysis, and you'll see it's virtually the same thing. And there's a thing called method of branch currents that only works in a certain condition in a certain circuit. I do not like laws or methodologies that only work in a certain type of circuit. To me, that's a waste. You might as well know a method that solves any circuit, which all of these do. Then, what I love is Thevenin's and Norton's. When I show you Norton's, you'll see that it does a kind of circuit. Now, for example, let me just show you a kind of circuit that if I asked you this, would you be able to solve this circuit? Don't try and do it, just think about it. You know the current flow here is 200 microamps. You do not know the value of that resistor. You know this is a 10K, and this is a 20K, and this is 15 volts, for example. What's the value of that resistor? Now, why is that hard to figure out? Because if you don't know the value of this resistor, you can't combine it with that, can you? If you can't combine it with that, how the hell do you know anything? You don't. By what I've taught you up till now, you cannot solve this circuit, can you? Period. It's an unsolvable circuit until, what is the thing that you do with Thevenin's? You remove the offending resistor. As soon as you remove that load, everything's cool. Then you make a Thevenin's equivalent, then you throw the load back on. But you'll find with Norton's, it makes this even easier. Norton's system deals with currents, and what you'll make is a current drive here, and you'll have a current source, a known resistor, and a current over there, so the way current splits. That's what Norton's going to do. I haven't taught you Norton's yet. It's very similar to the Thevenin's concept, but it works in circuits where you only have current issues, and that's a simply solvable circuit with a couple steps. You can solve that. But until I tell you that, how would you do this? If you didn't know Thevenin's or Norton's, it's an unknown component. How do you combine that with that? There's no way, because you don't know the value. How do you know how current splits? How can you know how current splits when you don't know the resistor values? Seems impossible, doesn't it? But it's not, because you can remove the offending resistor, get an equivalent circuit that allows you to see how current splits, and that's Norton's theorem. So, knowing Thevenin's, knowing Norton's, knowing mesh and superposition, there is no circuit you cannot calculate. That's why I picked those. It gives you the tools to find any possible circuit, yes.
With Thevenin's, we can find that, right, by removing the resistor.
Well, you can try.
The Thevenin's equivalent, and then you take the current and use your normal equations to find out what the resistance would be with.
Because current remains the same in all parts of the series circuit. Bingo. So could you solve that by Thevenin's? Well, I'll let you figure that out. But I have to go on to something else about this right now. So
you could use Thevenin's to solve it.
Maybe. I'll let you think about that. I'm going to show you how to solve it with Norton, because Norton's is cool. Okay, but now, the last topic today, we don't have to calculate the whole thing, but I'm going to show you how you can do it. I'll let you off at least a minute early today.
It'll take me 10 minutes to watch that.
I want to make a point about the T-type circuit. We did this kind of circuit with superposition. We did this kind of circuit with mesh, didn't we? I have a mesh handout there. We could solve this, I guess. Well, I'll do it by we have an answer to this one, it's small even numbers, so let me just show you it with this. R1 is 4 ohm, R2 is 12 ohm, R3 is 12 ohm. This was 36 volts, I'll call it VY. This is the X, and this was 20 volts. The answer, according to my handout sheet, was the voltage drop across resistor 2 was 19.2 volts, and the current flow through resistor 2, the middle resistor, was 1.6 amps. So this is from this superposition handout. So we already know the answer for that. We can also find the answer for the other resistors, but let's just work on resistor 2 right now. Could you solve this using Thevenin's? Of course. You remove the load. Which resistor makes this circuit look significantly less complex? Well, removing the center resistor makes it look like there's just a simple series circuit out here. And there is on your way to finding the Thevenin. If you just saw this, don't we have to find the voltage from A to B? Now this is important. The reason this is important is this is what everybody screws up on. Is could I redraw this circuit to look like this? sure the polarities are both going positive on the top. Yes, they are. Now, why would I bother to redraw the circuit like that? Where's point A and where's point B? Here's point A, here's point B. Is this point also point B?
Yes.
Is this point also point B?
Yes.
Is this point A?
Yes.
Is this point A? Yes. In other words, point B is anywhere along here. Point A is anywhere along there. By redrawing it like this, what could I say about, in terms of referencing or looking from point A to point B, how are these connected? Maybe this will help. Is that point A?
Yes.
Is that point B?
Yes.
How are these branches connected? In parallel, yes. From the perspective of point A to point B, they are in parallel with each other, aren't they? Would the voltage here to here have to be the same as the voltage from here to here? Absolutely. But to get there, is this also a series circuit?
Yes.
Is this a series circuit, yes or no?
Yes.
I want more people to
I don't
respond.
see it. I say no.
Yes.
What is the definition of a series circuit? You know current remains the same in all parts, but the other definition is?
One pound.
One path, very good. One path for the flow of current. Is there one path for the flow of current here?
No.
Yes.
Too close.
There's one path for the flow of current.
Oh,
Polarity.
polarity.
If the polarity wasn't,
Irrelevant. How many paths for the flow of current is there?
One.
Therefore, what kind of circuit is it? Series. If there's one path, can the current be different anywhere in that path? No. Now, is this the original circuit? No. It's getting to be Thevenin, so you got to separate it. See, that's the problem. That's where the brain starts to turn to mush at 10 o'clock at night. This is a methodology to get to a solution. You're trying to find V Thevenin. You're not looking at this as the original circuit. The original circuit has 3 friggin' resistors. You can't just say, I don't feel like having a third resistor. That's like, you got a car, and I don't feel like having a distributor today. But taking out the distributor allows you to work on the car, that's one thing, but you can't run the friggin' car without the distributor, right?
Yeah, you can.
Oh, shut up.
Yes, baby. Well, unplugged.
So,
Love you too, kid.
yeah. So, when you took this resistor out, it allows us, because we want to find V Thevenin, what do you have to do to find V Thevenin? You got to remove the resistor that offends you. So you remove it and you want to find the open circuit voltage between there and there. To accomplish that, the steps that we take now is simply to find the voltage from there to there. Now let me ask you this, what is the voltage from there to there? Wouldn't it be this voltage plus this voltage is from there to there because it's a series branch?
Yes.
Wouldn't the voltage from here to here be the voltage here plus the voltage here? So you have to determine what those voltages are. To do that, you have to be careful. Wouldn't you have to find the current flow in this resistor to find the voltage across it? Wouldn't you have to find the current flow here in order to find the voltage across it? Are these 2 voltage sources causing the current to flow in that circuit? Yes.
Yes.
Are they helping each other to put current in the same direction? Or are they opposing each other?
They're opposing.
They're opposing each other, exactly. Isn't this current, this voltage source trying to push it clockwise? This is trying to push it counterclockwise?
Subtract.
You have to subtract, exactly, and the biggest one's going to win. If I redrew the circuit for a moment, just to help compute, can I do this as I'm losing my pen? Is that the identical circuit to that when I don't put in A and B? Yes.
Yes.
You got a 4 ohm, you got a 12 ohm, so couldn't that be considered 16 ohms? And here you got 20 volts